So, hello, my name is Brett Morris, and I'm currently at NASA Goddard Space Flight Center, formerly University of Maryland, and I'm going to present to you some Kepler data, particularly on a hot Jupiter, which I promise I will try to motivate at AbGradCon, and a particular cool feature for it. So you've heard this a few times already. Fortunately, I don't need to give you too much background, but I'm going to try to put in enough again so that Daniel's talk makes a little more sense as well. Transiting exoplanets are what Kepler studies. There was the Doppler method, where you can see planet-hosting stars move towards you and away from you in spectra, but then also just by looking at the brightness of stars that host exoplanets, if their inclination of their orbit takes them in front of their star, you can see a decrease in the brightness of the star over time, and that's what Kepler does. Kepler has a very high precision photometer. The CCD on it is very good for measuring brightness changes, and it measures those changes for 150,000 stars continuously. For most of those stars, it measures once every half hour. For a select group of about 500, it measures once a minute, every minute for the 4 years that it took continuous data. So that's a lot of photometry, and we can get out a lot of cool effects from that. So far, the last time I checked, it was 3,200 candidate planets, so we're getting up there in the numbers. I'm going to talk to you about one planet in particular. It's called HAPP7b. They'll have these crazy names. Fortunately, mine doesn't have too many numbers. So HAPP7b is a hot Jupiter. And this is what the transit light curve looks like for HAPP7b. That's not a model. That's the data. And you get this particular transit light curve by taking each transit light curve that Kepler recorded over 4 years. Or in this set, I'm showing about 2 years worth of data. And you put them one over the other and overlap them, and then bin down the data so that you really bin out the signal to noise. So you get very little scatter in your data. I didn't show a fit here because the fit would have just been right on top of the data. You can't really see it on this scale. And the shape of the transit light curve tells you everything you know about the planet when you're doing the transit method. So what did we learn? We know that the period is 2.2 days. If you compare that to solar system planets, Mercury takes 88 days to go around the sun. This planet takes 2, so you can imagine this one's much, much closer. It's the semi-major axis of its orbit, which is the distance it orbits from its star, is only 4 times the radius of the star. It's nearly on top of the star. It's kind of sterile. So again, I'm going to motivate this later. The radius of the planet is about 7% of the radius of the star. It's pretty chunky. And its orbit takes it within 7 degrees of edge on from us, which is why we can see it in the transit method. So I did not show you a fit overlaid onto this transit light curve because it would be too close. But if you do that fit and then you subtract the data from the fit, you get these residuals, these leftovers. Let's note the scale of these leftovers. The residuals are in parts per million, to borrow a term from you chemists. And so these are very, very, very fine changes in brightness. Kepler was designed to measure about 10 part per million change in brightness because that's what you need to see an Earth radius planet at 1 AU, which was kind of the big goal of Kepler. There's a very questionable bump there. It's kind of a smear in the residuals. I'm not going to claim that that's a discovery of something amazing, but I'm going to ask what might that bump be? And we're going to talk about that a little bit. The model that we use to fit this is from Mandel and Egal, which really just considers the shadow of the planet on the star. It doesn't consider too many extra fancy things. So if you get residuals from that model, cool things could be happening, especially in this regime where the brightness changes are very small. So one way that you can get a positive bump in light curve residuals is by putting a dark spot on your star. If we imagine a big dark sunspot like that on our cartoon model, and the planet begins to transit, you get a dip in the light curve just like you would expect from what you just saw in the model. But as the planet passes over the dark spot, it's as though it didn't fully cover the star anymore, because compared to your other model, the star was darker there. And so you get a big positive bump in your light curve for this cartoon model. If it's a very dim bump, you only get a smaller dark spot that's not as dark, and you get a positive bump. What can cause dark spots on stars? You probably know about sunspots. Those are common on all kinds of stars, on particularly the sun, if you've ever gotten to observe it through a telescope on Earth. And star spots have a few qualities that we can use to wonder if they are actually the source of this dark spot. They only persist on the scale of a few weeks, and they happen at more or less well-distributed latitudes on most stars. And so it's probably not likely that our exoplanet transited over the same spot for 4 years continuously at the same point in its latitude. And you can measure the activity of a given star using spectral qualities of that star. And according to some studies, this isn't a particularly active star, so we wouldn't expect magnetically driven star spots to be quite active. Our referee on the paper that we put out mentioned that it could also be due to stellar rotation. If stars rotate really quickly, kind of like an ice skater with their arms getting pulled out, the outer layers of the photosphere of that star might get pulled away from the star. When that happens, if you get pulled away from the core, you cool off a little bit. Cooling off darkens the surface, and then the planet passing over the darkened surface could have leftover residuals in your light curve. But that would have caused a symmetric difference across the rotation of the star. We don't see that. We just see a little bump that's pretty localized. So how do we explain a small amplitude spot that's very localized and always seems to cross, the planet always seems to cross over it at the same time over 4 years? There's a very exotic effect that's a big claim, and so we're not claiming a discovery. We're going to claim a maybe this is what it is. And we say maybe it's planet-induced stellar gravity darkening. Gravity darkening happens when the tides of a planet pull the layers of the star towards the planet, kind of like the tides of the moon pull the ocean towards the moon. Except when a photosphere is pulled away from its star, as I mentioned a little bit earlier, getting pulled away means cooling down. Cooling down means getting dimmer. And so if there were a dim spot on the surface of the star that came from the planet pulling tides on the surface, on the photosphere, that dark spot would slightly lag the orbit of the planet, just like the tides of the ocean slightly lag the orbit of the moon, because it takes gas time to respond to the gravitational kick of the planet passing over it. And so you would expect that if the planet's rotating around this way, counterclockwise, or you would expect that the dark spot would be behind the planet in its orbit, which means viewed from down below, where our observer would be in this cartoon, the planet would transit the dark spot in between the beginning of the transit event and the middle of the transit event, which is where we see our spot. We can predict how much cooler the surface of the star is at the center of the dark spot compared to the rest of the star based on how much dimmer that spot is. So if this actually is what we're seeing, the effective temperature difference between the center of the dark spot and the rest of the surface of the star is 0.2 of a Kelvin. Gives you an idea why this is a bold claim. But this is the kind of thing that you can do when you have high-precision photometers like Kepler. Kepler can really give us really amazing science that we haven't seen from stars before. And a lot of stellar astrophysicists are having a lot of fun with the rebirth of their field, sort of, among younger people, because Kepler is giving them new things to look at. We can also then use first principles of photosphere physics that have been done by other scientists over the years to get an idea of how the gas in a photosphere should respond to a gravitational kick from a planet that orbits it. And if you measure up what we believe in the pressure and density of the photosphere of this star should be against how long it took the atmosphere to respond and create the dark spot, given by that phase lag, you can get an idea of whether or not the timing is consistent, because the timing is the parameter we can best constrain from where that bump was in the anomaly. And they match up to be more or less consistent, so our timing works out well. But this is maybe a 3 sigma detection, and if we want to actually claim anything, we need to wait a little bit longer. Unfortunately, there's more Kepler data coming in still that hasn't been run through the pipeline, even though Kepler is not collecting data currently. And so there's a little bit of hope that this model can be continued to be looked at. I'm going to talk to you a little bit about the Eclipse, too. We've heard it given a few names. That we had the occultation word before. Exoplanet scientists have had a fun time coming into the field of binaries, which have existed in astronomy for a long time, and trying to reinvent the vocabulary and calling occultations eclipses and eclipses other things. But I'm going to call this particular event the secondary eclipse. We've been talking about the transit event, which is when the planet passes in front of the star, which you get a nice big signal from. But when the planet goes behind the star, there's a very small effect that you can measure as well, as the planet's light gets blocked out by the star. And the light that you're seeing from the planet comes from thermal emission from the planet, and also from reflection of the starlight off of the cloud tops, essentially. This is what that light curve looks like for HAT-P7 if you sum up the 2 years of data. So the planet was going around behind the star, and then as soon as it passes behind the star, the light drops down to just the solar brightness, and then goes back up again after. We don't have crazy bumps to claim this time. One of the things we wanted to look at with this is if there's variability in the secondary eclipse depth, because variability in the depth of the secondary eclipse would be variability in how much light is coming to you from the planet. If you were to imagine looking at Earth transit or eclipse again and again from somewhere else, the amount of clouds on Earth's atmosphere would change how bright the Earth appeared to be. Clouds are very reflective. The ocean absorbs a lot of light. So what if the cloud tops on this planet were changing? What if their color changed? Kind of an interesting question to think about. This is a measure of the secondary eclipse depth over 355 eclipses. There's a lot of scatter, not a lot of anything interesting to talk about, which you could expect because based on the radius of the planet, which we constrain from the transit light curve, and where we know its semi-major axis puts it away from its star, we know how much light hits the planet. And then we can measure how much light we get from the planet to understand how much light is being reflected and how much is being emitted. If you do that, you come up with a very low albedo. Albedo is the fraction of light that comes back to you. Only about 3% of the light or less that hits the planet gets reflected to you. This is blacker than coal. It's a very dark planet. So most of the light you see in the secondary eclipse is just thermal emission because it's hot. We can also tell how hot it is then by how much light is coming back. It's about 2,700 Kelvin. It's pretty sterile. And there's no significant variations in how bright it appears to be. Now I'm going to try to motivate why I'm giving you a talk about this planet at AbGradCon. I promised you I would. So as Sukrut mentioned a little bit earlier, hot Jupiters are some of the easiest planets to observe in transmission and emission spectroscopy. They have big extended atmospheres that give us the best chance to get some signal. And so in our efforts to get spectra of super Earth-sized planets, ideally in one day, we need to kind of refine our methods on the bigger, easier targets. And since they have quick orbital periods, they're really easy to observe again and again and again and beat down your signal to noise, like you saw in the nice light curve that we had for this planet. But then there's also the question of dynamics. This planet orbits over the rotation axis of its star. So if its star rotates this way, the planet rotates kind of at 90 degrees to the inclination of everything in our solar system. So why is it doing that? How did it get there? To form a gas giant, it can't have formed at a distance of 4 stellar radii from the star. Something catastrophic must have happened to put it there. And so we can ask the question, if there were potentially habitable terrestrial planets in this system, they probably would have gotten kicked out in the event that put this planet where it is. So there's an interesting question of dynamics, too, that hot Jupiters raises in terms of questions of habitability of extrasolar planets. And I'd like to thank my mentors, Dr. Avi Mendel and Professor Drake Deming, and NASA Astrobiology Institute that I didn't put on here, everybody else.
Thanks very much.
Thank you.
And we have a few minutes for questions again.
Wait for a mic.
Why do you think that planet has such a low albedo?
I wish I had a cool answer for you. So one of the things you're seeing in the transmission spectroscopy is we don't know that we fully understand the compositions of these atmospheres very well yet. There's still a huge amount of uncertainty as to what's in these atmospheres. One of the best ideas right now as to why the albedo is so low is that if these atmospheres are very, very long columns of gases, kind of like the solar atmosphere, if you think about the sun, there's just this huge column of gas. And if the sun weren't shining, there's an immense column of gas that could just absorb lots and lots of light. And so that's kind of one of the only real ideas out there. We don't think it's covered in soot or something to really make it black, and even soot wouldn't make it that black. So there's a lot of questions about that. Yes.
So I was wondering if there was a moon orbiting that planet, like, could that, would you actually be able to pick up that signal and noise as well?
So there's going to be a talk on exomoons today, so I'm going to try not to talk over that speaker too much. But one of the ways that you would see moons in transit light curves, in potentially one of the more easier senses, is by trying to measure when mid-transit is. Moons orbit around a planet, and so you don't know if it's going to be on the left side or the right side of the planet when it transits. And so it could kind of drag your light curve down early or late, depending on which side of the planet it's on. So that would show up as a bump near our ingress or egress here, or a widening of the ingress and egress, because this is integrated over many years, so you just see it wider. So there would be ways to confirm that via spectroscopy of this planet later, but we don't see any evidence for that here. And chances are, you can imagine the Hill sphere, the radius around the planet at which things could orbit the planet stably, is very, very small because this planet is nearly on top of its star. So anything that could have been there one day is probably dynamically stripped away.
We're going to have to move on. Thanks very much.
Thank you.